Okay, everybody, welcome back. Today in Physics 44, what we're going to do is start a new chapter of the textbook. That's chapter 6 of Giancoli, and the topic of this chapter is gravity. So it's something we've talked about in the past, but in this chapter we're really going to dive into the details about how does gravity work. And the way I'd like to introduce you to some of the concepts and equations here is actually to give you a historical overview. So how is it throughout history that we went from sort of primitive and ancient ideas about the way things, let's say in the night sky, move around, like how do the stars move around the night sky, how do the other planets move around, and how we progressed from that early understanding to what we know today, which is gravity, a modern theory of gravity. So, to sort of give you a brief outline of that historical picture, let's go all the way back to the days of ancient Greece, in particular people like Aristotle in ancient Greece. What did they think about astronomy? What did they think about the way things in the sky moved around? And the really kind of big picture, most crucial point here is almost everyone at the time thought that the way things move here on Earth and the way things move out in the night sky, so for instance, if I throw a ball, it lands on the ground, there's some set of rules that explains how that motion occurs. And then if we have, let's say, the motion of a planet, like we're observing the planet Mars out in the night sky, it was thought that there was a fundamentally different set of rules for the way things move out there in the heavens compared to the way things move here on Earth. And that was just pretty much commonly accepted. Okay? So, what was the model of the universe back then that was commonly accepted? Well, it was something called a geocentric model, where geocentrism just means the Earth is at the center. So the model of the universe was the Earth is at the very center of the universe, and everything moves in perfect circles around that. So for instance, the moon moves in a perfect circle around the Earth, Mercury, that planet, moves in a perfect circle around the Earth, so does the sun, and so do all of the different stars in the universe. This was the model at the time. And one thing I want to highlight about this model is perfect circles, okay? For whatever reason, people at the time had this idea that motions here on the Earth were quote-unquote imperfect, but motions out here in the heavens, where the stars and the planets exist, were perfect. So it was thought that everything has to move in a perfect sphere because, again, there's a fundamentally different way things work here on Earth compared to out here in the heavens. So that was the thinking at the time, and as we're going to find out, all of that is completely wrong. So let's go to the next step in history where, even astronomers way back in the times of ancient Greece noticed a problem. And that problem was something called retrograde motion. So retrograde motion is the following idea, is that if you observe, let's say, a planet, maybe Mars, in the way it moves across the night sky over several days, you're going to notice that it actually appears to move in one direction for a while, and then suddenly reverse its direction, and then reverse its direction once again. So this reversal of the motion of a planet as we observe it in the night sky, that's called retrograde motion. And notice how the geocentric model of the universe cannot possibly explain retrograde motion because everything's just moving in a circle in the same direction. Things don't kind of reverse their direction. So as it turns out, this was a big problem, and the geocentric model had no way of explaining it. So what eventually happened is people said, well, maybe the Earth isn't the center of the universe, right? Maybe there's a different way to explain this sort of phenomenon. And so people came across the idea that, no, the Earth isn't just at the center of the universe, it's actually moving around the sun along with all the different planets. And this is able to explain retrograde motion. So let me show you in this animation how this works. So what you're going to see here is this inner planet represents the Earth, and you're going to see it going in a circle around the sun. Then this outer planet is just like another planet, let's say Mars, that's also orbiting around the sun. And let's see what that looks like when we see what happens. Okay. So I want you in particular to look at this line right here, which basically traces how we would see this planet against the background of stars, because overall, because after all, that is, that's how we observe the way planets move around the sky. We observe them against the backdrop of the stars. And if both the Earth and other planets are moving in circles around the sun, you can see right here that we're going to see this retrograde motion where the planet appears to sort of reverse direction as it orbits. Okay, so the point to take away here is retrograde motion gives really strong evidence against this geocentric or Earth-centric model of the universe. Okay, so now let's fast forward several thousand years in history to the time of Nicholas Copernicus, who lived in the 14 and 1500s, who was a really big advocate of what we call the heliocentric model of the universe. So heliocentric just means the sun is at the center and everything moves in a circle around the sun, as opposed to everything moving around the Earth. And okay, what does this model look like? Well, you've got the sun at the center, you've got all the different planets moving in circles around the sun, and as we saw previously, this is able to explain retrograde motion. So there's a really good reason to accept this model as opposed to anything else. And as further evidence against the geocentric model of the universe, Galileo, who lived about 100 years after Copernicus, showed that the planet Jupiter actually has moons that are orbiting it. So let's think about that. If the Earth is at the center of the universe and everything is orbiting around the Earth, how could Jupiter possibly have any moons that go around it? Right? So it's really not the case that Earth is the center of all motion in the universe, right? That's what Galileo showed, in addition to this idea of retrograde motion. And it's really hard to overstate how important this was in this shift in thinking from people thinking that the Earth was at the center of the universe to the sun being at the center. That was a massive shift. And it was called the Copernican Revolution, when people really started accepting this idea that it's really the sun that's at the center. Now, I don't want to make it seem like Nicholas Copernicus, who is only, lived about 500 years ago, he wasn't really the first person to suggest this idea that, the sun is at the center, not the Earth. But he was a really big advocate of it, and he started this revolution that got people to really accept this idea. So he gets the credit, even though people way before Copernicus were saying that this should be the case. Okay, so there you go. That's the heliocentric model. Notice all the planets are orbiting around the sun. Now, if we fast forward ahead in time to someone named Johannes Kepler, who lived in the late 1500s and early 1600s, this is where we're getting to what we call modern science, where it's really driven by observations and taking a lot of data and making sure that any theory we have about how the universe works really matches the data. It's really verified by the data. So what Johannes Kepler did was he studied a huge amount of data, tracking the motion of all the different planets in the solar system. He really studied it closely, looking for any kind of pattern that he could find. And out of that, he discovered 3 laws of planetary motion, which really accurately describe the way the planets move. Okay, so in fact, Kepler's 3 laws of planetary motion are still valid today. You can still use them today to make calculations, because they really work. But we're not going to get into Kepler's 3 laws just quite yet. We're going to do that at the end of the lecture, but just want to kind of add this to our historical picture. And really the importance of Kepler is he brought an entirely new level of mathematical precision to astronomy, right? He had really precise data. His ideas really matched the data better than anyone who came before him, okay? Now, one thing that Kepler was really never able to do was describe why the planets move the way that they do. So in other words, he had a pretty accurate description of how they move around, but he was never able to find any kind of mechanism. What's actually causing them to move around the sun like this? He had no answer to that question. And that's where Isaac Newton comes in. So Isaac Newton, who lived from the mid-1600s to the early 1700s, developed a theory of gravity, and Newton's theory of gravity was able to explain everything that came before him. So why Kepler's laws are true, and why does everything in the solar system move in the way it does. Newton was able to explain all of that. Okay, so that's the historical picture, and this is sort of the model of our solar system that you get with Kepler, where again everything is moving around the sun, and it moves around the sun in a very specific way that we're going to learn about at the end of the lecture. Okay, so that was most of the historical picture. Now we're in the time of Isaac Newton, and let's talk about the theory of gravity that Isaac Newton developed called the law of universal gravitation. And we're actually going to go into some of the calculations that Newton himself made to discover the law of universal gravitation. Okay, so you may have heard of this story that one day Isaac Newton was sitting under an apple tree, and he was kind of pondering this question as to how does the moon orbit the Earth? Why is it that the moon seems to go in a circle around the Earth? What causes that? And as he was thinking about this question, the legend has it that an apple fell out of the tree and hit him on the head. And it was when the apple hit him on the head that he had this moment of realization, this moment of insight, where he realized the answer to his question and he figured out how gravity actually works. Now, I don't know if this story of the apple tree is actually true. I don't think there's any way to verify this. I think it makes for a good story, so let's just sort of go with it. But what was that realization that Newton had? Well, what Newton realized is the force that keeps the moon in orbit around the Earth, okay, if the moon is going to be in orbit around the Earth, he realized that there's some kind of force pulling the moon towards the Earth. He realized that that force is the same exact force as the force that causes the apple to fall to the ground. That's called gravity. And this is a really, really important point because what he showed ultimately is the way gravity works here on Earth, okay, and you see something fall to the ground. It's the same exact way as it works out there in the heavens, okay, which was a really big shift in thinking because, as I said earlier, before Newton, it was really commonly accepted that the way things move here on Earth and the way things move out there in the heavens were just completely different. Two different sets of rules. Newton did what's called unification. He showed that the way an apple moves as it falls out of a tree is the same as the way the moon moves around the Earth because it's all explained through this idea of gravity. That's unification, where you take many different ideas that seem to be unrelated at first, and you explain them in one nice little package. That's unification, and that's really what physics is all about. We're trying to explain as many different things as we can in as little, in as simple a set of rules as we can, okay? So I want to give you actually one more example, just real quick, of unification in physics. So back in the early 1800s, it was known that there was this effect called magnetism. People knew that if you take two magnets together, they attract, and then if you put them together in another way, the magnets might repel each other. There was also this idea of electricity that was known. People also had some idea about what light is. Then, this guy named James Clerk Maxwell, in about 1860s, around that time, showed that magnetism, electricity, and light were really all the same thing. He was able to explain all of those things with a single theory. Again, that's just another example of unification in physics, where we take a bunch of separate ideas and we explain them all in one fell swoop. And Newton was really the first person to do this. Okay. So, Newton had this kind of thought experiment. Obviously, he wasn't able to do this in the real world, but it's kind of a thought experiment. We're going to imagine that we have an absolutely huge cannon just sitting somewhere on the Earth, and it can fire out projectiles horizontally, and we're going to ignore air resistance. Let's just say that the cannon is so high up that it's basically above the atmosphere and there's no air resistance. Okay? So what we're going to do is we're going to fire the cannon, and what we're going to see is the cannonball is going to fall to the ground, something like this. But what happens if we fire the cannonball with a larger speed the next time? Well, it's still going to hit the ground, but somewhere a little bit further out from where the cannonball was launched. Something like this. Okay. Now let's keep ramping up the speed. Let's make it go faster and faster and faster. Until at one point, we fire the cannon so fast that the cannonball actually never hits the ground at all. Instead, it's in orbit around the Earth. Okay? So eventually, if you fire it fast enough, the cannonball is moving so fast that the curvature of its path is exactly matching the curvature of the Earth. So even though it's being accelerated towards the Earth, it never hits it. Instead, it's in orbit around the Earth. Okay, so that's how we get something in circular orbit, basically. You just have to fire it out fast enough so that it never hits the ground. That's a circular orbit. So, okay. Let's think a little bit more about circular orbits. So, what does Earth's gravity actually do to a projectile? Let's say I fire a projectile like this with some initial velocity v naught. Well, we know that if there were no gravity, that there would be no force acting on this projectile, so all that would happen is it would move in a straight line like this. This is the straight line path it would move in if there were no gravity. But since there is gravity, which pulls the object down towards the Earth, the actual path is shown here in red, and it's sort of curved away from this straight line path. Okay? Now, at the same time, as this projectile is moving, it's moving over the Earth, and the Earth itself is actually, spherical, it's curved. And so, if the Earth itself curves away just the same amount as our projectile is curving away from that straight line path, well then it's never actually going to hit the ground, right? Because this curvature matches this curvature, they never intersect. The projectile never hits the ground. So, actually, what we're dealing with in this case, when something is in circular orbit, is an object that has what we call a centripetal acceleration. Remember, anything that moves in a circle with a constant speed has an acceleration v squared divided by r. So we can actually apply that idea to a circular orbit. And so, to summarize, what Newton realized is that an object that's in circular orbit is actually in free fall, just like anything else you might see. If I, toss this paperclip across the room, it's in free fall. If I have an object in circular orbit, it's also in free fall. It just never hits the ground. That's the only difference. So, we're dealing with objects in free fall with acceleration v squared divided by r. That's really what a circular orbit is. So the next thing we're going to do is get into some of the calculations that Newton made to try to figure out how gravity works. Okay? So the first thing I'm going to show you is some numbers that were known to Newton at the time. So in Newton's time, the distance to the moon, which I'm going to call lowercase r, it was known. Okay, I'm not going to get into how that was known, but let's just put the number on the slide. It's about 3.8 times 10 to the 8 meters. That's about how far away the moon is. Okay? Another thing that was known was the radius of the Earth. So I'm going to use capital R for the radius of the Earth, and that's about 6.4 times 10 to the 6 meters. The last number that we're going to put into here is the period of the moon's orbit. So that just means how long does it take for the moon to go around the Earth in a circle one time. It's a little bit over 27 days. And if we convert that to seconds, the time is 2.4 10 to the 6 seconds. So that's, again, how long it takes for the moon to go around the Earth one time. These are the numbers we're going to use. These are the numbers that were known at Newton's time. Okay, so when we think about the moon orbiting the Earth, we'll think about it moving in a circle like this, and its velocity vector is always going to be tangent to that circle. This is just how circular motion works, as we learned back in chapter 5. The acceleration is always going to be pointing inwards towards the Earth, towards the center of that circle. Again, something we learned back in chapter 5. Now, real quick, it turns out the moon doesn't move in a perfect circle. It's more of an ellipse, so it's not a perfect circle. But treating it like a perfect circle is close enough for our purposes. Okay? All right, so the first thing we're going to do here is calculate the speed of the moon in its orbit. Okay, well, speed is the distance traveled divided by the time. And we can think about distance over time in the following way. The distance it moves, let's have that be 1 circumference, or 2 pi times r. Now, the time is going to be the period, because that's how long it takes to go in 1 full circle around the Earth. So if we take the circumference divided by the period, that's going to give us the speed. And we can just directly plug in the numbers now, because we have 2 pi times 3.8 10 to the 8 meters. Again, that's the distance between Earth and the moon, so that would be the radius. And then the time would be 2.4 10 to the 6 seconds. So go ahead and try to work that out. And what you should find is about 995 meters per second. So the moon is traveling at almost a kilometer per second as it orbits around the Earth. So it's moving quite fast. And what can we do with that? Well, we can calculate the centripetal acceleration of the moon, because we have the speed, we have v, and we also have the radius. So remember that centripetal acceleration is given by v squared over r, so that would be the acceleration of the moon right here. And now let's plug in what we just calculated. 995 meters per second is the speed. Square that, divide by r, which is again 3.8 times 10 to the 8 meters. What kind of acceleration do we get? It's actually not much at all. It's really small. It's 0.0026 meters per second. Okay, so we've got a number telling us what the acceleration of the moon as it travels in a circle around the Earth is equal to. What can we compare that number to? Well, we can compare it to what we call g, or the acceleration of free fall for something close to the Earth. So let's see how that works. So the moon accelerates towards the center of the Earth at a rate of, let's call it a moon, acceleration of the moon, 0.0026 meters per second squared. Now, that's the acceleration of something that's way, way out here, so not anywhere near the surface of the Earth. However, if I had an object that was right at the surface of the Earth, so just quite literally imagine dropping something that you have in your room, well, it accelerates at 9.8 meters per second squared. Okay? So we know the acceleration of something that's way, way out here. We know the acceleration of something that's right at the surface of the Earth. That's a useful comparison to make, so let's do it. Let's take the ratio of a moon divided by g. So take this number divided by this number, take 0.0026 divided by 9.8, and rather than giving you this as a decimal, it's really, really close to 1 over 3,600. So just verify that that's true. When you take the ratio of those two numbers, it's about the same as 1 over 3,600. The other comparison we can make is this. Let's compare the distance here, all the way to the moon, with the distance of something that's just right at the surface of the Earth. And in particular, I'm talking about distance from the center. Okay, so it's one radius to go from the center of the Earth to the surface of the Earth. It's this big distance we've been using, our moon, 3.8 10 to the 8 meters, to go from the center of the Earth to where the moon is. Let's compare those distances. Okay, so if we take the radius of the Earth divided by that distance to the moon. Again, try to make the calculation, see what you get. It's roughly 1 over 60. Okay, so again, crunch these numbers, verify that it's about 1 over 60. And once you're convinced, there's something really striking about these numbers. So take a look at it, try to figure out what it is, and what you'll notice is, if I square 60, I get 3,600. That is no coincidence. Let me explain what that's all about. Okay. So basically what Newton realized is, if the distance from Earth's center increases by a factor of 60, so the distance increases by a factor of 60 as we go from here to here, the force of gravity, okay, the effect of gravity decreases. Not by a factor of 60, but by a factor of 60 squared. Okay? So what Newton just realized is the force of gravity follows what we call an inverse square law. Meaning, the force of gravity gets weaker with distance. So gravity right next to the surface of the Earth is way, way stronger than gravity all the way out here where the moon is. So it gets weaker with distance according to 1 divided by distance squared. So the force of gravity is proportional to 1 divided by distance squared. That's the idea. That's the entire theoretical framework for Newton's theory. Okay, so now, since hopefully you kind of get a sense of what Newton was thinking at the time when he came up with this law of gravity, which describes gravity as following an inverse square law, let's just state exactly what this looks like. So Newton's law of universal gravitation says the following. Every particle in the universe attracts every other particle in the universe with a force that is proportional to the product of the masses and inversely proportional to the square of their separation. Okay, so let's get into that just a little bit now. The basic idea that you should have in your mind is that if I have a mass m1 right here, and another mass m2 right over here, they're separated by some distance. So the distance between them, from now on, we're going to call that r. Okay, so r is the distance between m1 and m2. The law of universal gravitation is saying it doesn't matter what these two masses are. They can be absolutely anything. They're going to be attracting each other with a force of gravity, and that force of gravity is, again, proportional to the product of the masses, inversely proportional to the square of the distance, or the separation. So, you know, this is kind of how Newton would word things back in his day, right? Just, it's a little bit wordy. How about we just put that into a nice equation? We say that the force of gravity is equal to g times m1 times m2 over r squared. Okay, so those are the two masses, right? It's proportional to the two masses multiplied together, inversely proportional to the distance between them squared. So that's why m1, m2, and r squared are in the equation. But there's also this g there. Okay, so let's think about it. Whenever we have proportionality, okay, so force is proportional to m1, m2 over r squared, you need a constant of proportionality in the equation. So that's what g is. G is just some constant that describes exactly how gravity works. And g, I'm going to give you the value, is equal to 6.67 times 10 to the minus 11. And the units here are a little bit funky. Newtons times meters squared divided by kilograms squared. Okay? So, let's go to the document cam real quick to flesh out some of the details. Okay? So, the first thing is, so Newton showed us that the force follows an inverse square law. So in other words, the force is proportional to 1 over r squared, basically by studying the orbit of the moon. Okay, so I already kind of explained how we got this inverse square law. It's by studying the orbit of the moon. But you might also ask, how did he figure out, or how do we know, that the force is also proportional to the masses, or the product of the masses in particular? Well, for this, let's just sketch out a little diagram. If this is M1, or no, let's say this is M2 over here, and this is M1 over here on the right. We know there's going to be a force of attraction. Okay, they're going to be attracted to each other. That's how gravity works. So let's draw a force here. This is saying that there's a force that 1 exerts on 2. Okay, so this is the force that mass 1 exerts on mass 2. At the same time, we know that there's going to be a force that mass 2 exerts on mass 1. So there's mutual attraction. They're getting pulled towards each other. And, okay, well, what do we know about these forces? I know that, let's say F12, it's got to be proportional to M1. So the bigger the mass that's pulling it, the more force we're going to have, right? That's the idea. But that also works the other way. I know that F21 is going to have to be proportional to M2, right? So the force that this guy is experiencing should depend on this mass, because again, the more massive this is, the more it's going to be pulling this one. So we have that the force that 1 exerts on 2 should depend on mass 1. The force that 2 exerts on 1 should depend on mass 2. But remember the third law, okay? These two forces have to be equal in magnitude. Okay, so if 1 exerts a force on 2, then 2 has to exert a force back on 1, which is exactly as strong. So actually the force can't just depend on M1 or M2 by itself. It has to depend on both M1 and M2. So that's kind of how this was reasoned out. And the last thing is the weird units on this constant G. So the force is given by this constant G times M1, M2 divided by R squared. So let's take the equation and solve for G. So G is equal to, let's multiply by R squared, so on top we'll have FR squared, divide through by M1, M2, and we have G is equal to FR squared divided by M1 times M2. All I care about here are just the units. So the force is going to be measured in newtons, R squared is going to be measured in meters squared, and then if I have two masses, well, that's going to be in kilograms for each one, but square it because we have two factors of mass. So that's where the units come from, as far as why is it measured in newtons times meters squared over kilograms squared. That's why. All right. So now what we have is an equation that describes the force of gravity between any two objects in the universe. Doesn't matter what they are. And so, what I want you guys to do is work out this problem. Estimate the force of gravity that the person sitting next to you in class exerts on your body. Give your answer in units of newtons. Okay, so just so happens we're in a time now where everyone is just working at home, we're not in class. But just imagine what it typically looks like when you are in class, right? So think about what the mass of you and the other student are going to be, and the separation, the distance between you two. And also just note that this number G is a constant. We know the value, it's right here. And try to estimate the force of gravity. So pause the video, work it out, and then once you think you have an answer, let's come back to it, and then we'll go through it. Okay, so now that you're back, let's go through it. The force of gravity is given by G, M1, M2 divided by R squared. That's how it works. Okay, so let's put some numbers into this. We know that G is equal to 6.67, 10 to the minus 11, newtons times meters squared divided by kilograms squared. Let's put the masses let's set some values for the masses. So let's suppose each student is 75 kilograms, which is pretty reasonable for an adult human. So M1 and M2, let's just set them both to be 75 kilograms. All right, well, what about R? That represents how far apart you are from the student that's sitting next to you. And again, we're not really trying to get super precise here. Let's say that the separation is 1 meter. So the distance between you and the person next to you, if you're sitting in class, is about 1 meter. I think that's reasonable. And so the force is going to be, actually let's do this down here. We have the force equal to 6.67 10 to the minus 11 newtons times meters over kilograms squared. Okay, M1 is going to be 75 kilograms. M2 also going to be 75 kilograms. That's both masses. Divided by the distance, which is 1 meter, which has to be squared. Okay, now let's first think about the units. I've got kilograms squared here on top, but that's immediately going to cancel with kilograms squared here on the bottom. I have meters squared here on top, but that's also going to cancel with meters squared on the bottom. So we're going to get a force in newtons. And the actual value that you'll get if you crunch these numbers is about 3.75 10 to the minus 7 newtons. So that's actually a tiny amount of force. And that's exactly what you'd expect. If you're sitting next to someone in class, technically, there's a force of gravity between you. It's just that it's such a small force of gravity that we typically ignore it. So for everyday sized objects, we're just going to ignore the fact that there's this gravitational pull, right? Like if I'm sitting next, or if I'm standing here right next to the screen, for instance, there's a gravitational pull between me and the screen. It's just so small that I don't really need to think about it most of the time. However, there is a force of gravity that we do have to think about when we're standing on the surface of the Earth. So let's think about what force of gravity does each student feel from the Earth? Okay, well, this is given by W is equal to m times g. Whenever we talk about the weight, we're talking about the force of Earth's gravity acting on an object. Okay, so if I have a 75 kilogram object, and then multiply by 9.8 meters per second squared, what I'm going to get is 735 newtons, which is not a small amount of force anymore, right? So let's compare. The force of gravity from the Earth is about 700 newtons. The force of gravity that two students sitting in class exert on each other is about, on the order of 10 to the minus 7 newtons. How much bigger is this than this? Well, it's about 2 billion times bigger. And so I'm just kind of demonstrating why we don't neglect the force of gravity from the Earth. That's typically a pretty large force. It's pretty important most of the time. But what we can do is neglect the force of gravity that everyday sized objects exert on each other. And that's what we almost always do. Okay, so that was an example. Hopefully gets you thinking about gravity. And now that we've done that example, let's think about it in context. To do that calculation, or any other calculation using the law of universal gravitation, we need to know what this number g is equal to. So big G, okay, is called the universal gravitational constant. And what it tells us is how strong gravity is compared to other forces in the universe. Okay? Now I really want to emphasize that big G that you see in this equation is not the same as little g that we've seen in the past, indicating free fall acceleration. This big G is a universal constant. So anywhere in the universe, if you want to describe how there's a force of gravity between two masses, M1 and M2, it could be the moon and the Earth, that could be your M1 and M2. It could be the Earth and the Sun, that could be M1 and M2. It could be the Andromeda Galaxy and the Milky Way Galaxy. Doesn't matter. It always follows this equation, and the constant G always has this value. Okay? So that constant G of 6.67, 10 to the minus 11 newtons times meters squared per kilogram squared, this is just a number for the whole universe. It's a universal constant. Everywhere in the universe, that's the value. So that's actually kind of a mystery. Why is it that we happen to live in a universe where G has this value and it doesn't have some other value? We don't know the answer to that. It's still a mystery. But what we can do is kind of imagine what would it be like to live in a universe where G had a different value. Okay, so let's start by imagining a universe where G had a much larger value than it actually does. Okay? And so basically by giving G a larger value, we're making gravity a stronger force than it was before. And so if you actually kind of dial up the strength of gravity in our universe, well, that presents a problem, because big structures like stars, planets, galaxies, okay, if gravity were too strong, they would just collapse into black holes. Okay, so we wouldn't have planets and we wouldn't have stars and galaxies, because everything would just collapse into a black hole if G were too big. Okay, on the other side of the spectrum, what if G had a value that was much smaller than this? Okay, and gravity was much weaker than it actually is. Well, turns out in our universe, you need gravity for things like planets, stars, galaxies to clump together in the first place. It's gravity that pulls them together to form a big structure. If gravity is too weak, then you'll never form those big structures in the first place. Okay? So we happen to live in a universe where gravity is just right. It's not too strong so that everything collapses into a black hole. It's not too weak so that structures never form in the first place. It's just right. And I'd like to just end this slide with a quote by a famous physicist named Lisa Randall. I think she's at Harvard. And the quote is this: "You might find it hard to imagine gravity as a weak force, but consider that a small magnet can hold up a paperclip even though the entire Earth is pulling down on it." So that's actually kind of remarkable, right? If you take a magnet and you hold a paperclip up to that magnet, the entire Earth is pulling down on that paperclip. The only thing that's pulling up on it is this tiny little magnet. And somehow this tiny little magnet is beating the Earth in terms of the force it exerts. So gravity is really weak, okay? It takes a lot of mass, something like the Earth itself, before gravity becomes important, right? It's weak enough that the gravity between everyday sized objects like you and the person sitting next to you in class is completely negligible. So gravity is in fact kind of a weak force. Okay, a little bit more history here. So far I've said we have the law of universal gravitation that was discovered by Isaac Newton. And in that equation there's this constant, big G, which basically tells us how strong gravity is in our universe. But it's important to note that it wasn't actually Isaac Newton that figured out what the value of big G is. That was someone else. So actually Isaac Newton never knew what the value of big G is. That was past his time. So back in the very late 1700s, after Newton was already dead, this guy named Henry Cavendish performed a really intricate experiment to measure the value of G, and what he used was something called a torsion balance. That's shown in this diagram. Okay, so this is Henry Cavendish looking all dapper in this picture. This is his torsion balance in this upper diagram. So basically here's what's going on. You have a string or a cable that is suspending this, this wire, and on either end of it you have two masses. So two lead spheres here and here, okay? you have another platform which is also containing two lead spheres here and here. So now let's just think about what happens if I have these two masses close by and also these two masses close by. Well, they exert a gravitational force on each other. It's really small, so it's hard to measure this, but they do exert a gravitational force on each other. And what that does is it causes the masses to come together, to get closer. When they get closer, this wire, it twists a little bit. So if we can measure exactly how much this wire is twisting, because these masses are getting closer together, then we can figure out what the value of G is. That's the idea. Okay, so the idea is, if we're going to measure the amount of twisting in this wire, it's so small that you can't just look at the wire and see it twist. You have to do something else, because the amount of twisting is so small. So what we have is a light source. It shines onto a mirror right here, and this mirror is actually attached to the wire, so it's twisting along with the wire. So basically, if the light source comes in and the wire twists, then it's going to reflect off the mirror. This light is going to reflect off the mirror in a slightly different place. So we're going to see this beam of light that's reflecting off the mirror kind of move back and forth because the wire is twisting. And just a really tiny amount of movement of that light is how we figure out that the wire is twisting. Okay, so Cavendish was able to calculate G because he knew the masses, he knew the force between them, and he knew the distance between them. Okay, so that's sort of in a nutshell how it was done. And now I just want to show you an animation of what this looks like. Again, we've got the twisting wire right here with a mirror, a light source shining towards the mirror, and then what happens next? Okay, so there's an attraction between the lead spheres. It causes the wire to twist. That causes this light, which projects onto this scale here, to move around. That's how we detect changes in the wire. Okay, and that's how G was measured. All right, so the next thing we're going to do is a quick example using the law of universal gravitation, or LUG. And here's the example. We have 3 point masses arranged in an equilateral triangle with a side length of 5 meters, as shown below. Okay, the masses are as follows. M1 is 15, M2 and M3 are both 25. What we're going to do is calculate the total gravitational force on M1 due to the other two masses. So let's work it out. Okay, so we'll draw on a diagram the forces on M1. Okay, so this is our mass, M1. And remember, we have these two other masses in a triangle down here. And so it's going to feel two different gravitational forces. It's going to be attracted to this mass on the lower left-hand side. So what do we call this force? Well, it's F21, because it's the force that mass number 2 exerts on mass number 1. We have another force going this way. What do we call it? F31. It's the force that mass number 3 exerts on mass number 1. Again, it's attracted to both of them, so they're two different forces to think about. Now, okay, it looks like what I'm doing is adding two different vectors, and then I have to add those vectors to find the total force. So part of this is going to involve some trigonometry. So here, let's think about it. This total angle between this force and that force is 60 degrees, because in an equilateral triangle, we have 60 degrees inside each interior angle. But actually, if I draw this little vertical line, I can split that into two. So I have 30 here and 30 here. So each one is going to be 30, they add to 60 degrees, because again, that's the angle inside of an equilateral triangle. The next thing we'll do is draw the x and y axes that we'll use for reference, just like that. And so here, what are the angles, okay, for these two force vectors, but relative to the positive x-axis? So what are the angles off the positive x-axis? Because this is what we're going to use to break the forces into components. Okay, well, the angle for the first vector, the one I'm calling F21, well, if I were right here, I would be at 270, but I'm not quite there. I'm 30 degrees short of that. So I'm at 270 minus 30, which would be 240. Okay, so the angle for this vector off the positive x-axis going like this, it would be 240. For the second vector, the one I'm calling F31, the angle is, well, I'm at 270 degrees if I'm down here, and then if I go an additional 30 degrees, so 270 plus 30, then I'm at this force, and so that's 300 degrees. Okay, so those are the two angles. Now what we'll do is we'll calculate the magnitude of these two forces. So the magnitude of the force, F21, it's going to be given by the law of universal gravitation. It's going to be big G times m1 times m2 divided by r squared. And I'm going to call this r12. So it's the distance between mass 1 and mass 2, and we have to square it. So we can actually calculate this pretty straightforwardly because, well, G is 6.67 10 to the minus 11 newtons times meters squared per kilogram squared. Okay, M1 is, let's see, 15 kilograms. M2 is 25. And what's the distance between them? Well, that's just the length of this side of the triangle to get from 1 to 2. I need to know the distance between them. And that was just given to us as 5 meters. So I have 5 meters squared right there. And what does this work out to? Well, it's a really small force because, again, these are pretty much everyday sized objects. So we have 1.00 10 to the minus 9 newtons, and we'll keep 2 sig figs right there. So that's the magnitude of the force between 2 and 1. Okay, the magnitude of the force between 3 and 1, what's that equal to? Well, it's G, M1, M3, because those are the two masses now, divided by R13, so the distance between 1 and 3. Now actually, I could calculate this again, but notice all of the numbers are the same, because G is the same as before, M1 is still 15, M3 is also 25, just like this, and the distance between them is still 5 meters. So it's the same exact magnitude for these two forces, 1 times 10 to the minus 9 newtons. Okay, so now we're going to add the vectors. So how do I add these vectors? Well, I'm taking F21 plus F31. That's the total amount of force acting on mass number 1. And the way I add any two vectors, as you remember, is break each one into components. So the first vector has a magnitude of 1.00, 10 to the minus 9 newtons. Now if I multiply by cosine of the angle, which is 240 degrees, that's the x component of that vector. The y component is the same thing, except multiply by sine of 240. So that's the vector broken up into x and y components. The next one, same exact magnitude, so 1.0, 10 to the minus 9. And then if I want the x component, I have to take cosine of 300, and then multiply by I hat, plus 1.00, 10 to the minus 9, sine of 300, multiply by j hat. Okay? So that's what we're doing. We broke each vector up into components. So what we do is we add the x components together, and then we add the y components together, and we'll see what happens. Okay, so adding the x components. Type into your calculator 1 times 10 to the minus 9 times cosine 240 plus 1 times 10 to the minus 9 cosine 300. Just add this. Well, you're going to find it works out to exactly 0. When you do the addition of the y components, like this, what you're going to find is you get minus 1.73 10 to the minus 9 newtons, and the negative sign is telling you that the force is going down. The fact that there's no x component makes sense, because if you look at these two vectors, it looks like their x components would just cancel out, right? But their y components would contribute to each other to give you an overall force going down. So the answer is the force is 1.7, 10 to the minus 9 newtons going down. So that's how that works. All right, let's go through another example here. I've got 2 point masses, M1 and M2 are both 15 kilograms, and they're separated, let's see. Actually, no, sorry, I wrote this wrong. M1 is going to be 15 kilograms, M2 is going to be 25 kilograms, okay? So that's M1, M2. And they're going to be separated by 4.5 meters, okay? The question is, if I have a third mass, M3, where would I have to put this third mass so that the net gravitational force on it is equal to 0? Okay, so let's think about this kind of conceptually. If I have this mass here in the middle, well, it's going to be pulled to the left by mass number 1. It's going to be attracted to this one. And it's also going to be pulled to the right towards mass number 2. Okay, so it's going to be pulled in each direction. If it's being pulled equally hard in both directions, then there's 0 net force. So we're going to figure out where does it have to be placed so that there isn't any overall force. Okay, so we'll go through this one. So just to reiterate, the basic picture is you have M1, and then some distance d away from that, you have M2. And then somewhere in the middle of those, you have M3, the distance x away from M1. That's the setup right there. So let's draw the forces acting on M3. So it's going to be pulled to the left, as we said, by mass number 1. So we could write this force as F31. And at the same time, it's being pulled to the right by mass number 2. So we can call that force F... this should be F13, because it's the force that 1 exerts on 3. And this should be F23, it's the force that 2 exerts on 3. Okay, there it is. And then we're saying if the net force is 0, that means I add these two forces together and I get 0. So the only way for this to work is if the vectors pointing in opposite directions exactly cancel each other out. Okay, so here, F13, F23 must cancel out. And the only way for that to happen is if they're pulling with the same magnitude. So the magnitude of F13 is the same as the magnitude of F23. That's the only way for them to cancel out. Okay, so that's what we have to work with. Okay, so for F13, well, I can think of this as G, mass 1, mass 3, those are the two masses, divided by the distance between them, R13 squared. Okay, for F23, that's the force between 2 and 3 right here. I'm going to have G times M2 times M3 divided by R23 squared. So I'm just applying the law of universal gravitation to each one of these forces. And let's cancel some things out. G, doesn't matter. M3 goes away as well. And now let's do a little bit of extra work. We have, so what can I say about R13? It's the distance between 1 and 3. Well, that's what I'm calling x on my diagram, and that's exactly what I'm trying to figure out, what x is. What is the distance between 2 and 3? Well, that would be this distance right here between 2 and 3. You can think of that distance as being d minus x. So if I take this full distance and I subtract off x, then I have the distance between 2 and 3. So that's why I'm saying the distance between 2 and 3 is d minus x. All right, so what we're left with is m1 divided by x squared equals m2 divided by d minus x squared. And here's the thing. We know the distance d, that was 4.5 meters. We know the masses m1 and m2, so we can solve for x. So here's how I'm going to go about solving for x. So first, I'm going to multiply through by d minus x squared on both sides. And then I'm going to divide by m1 on both sides. So what I'm going to get is d minus x squared over x squared equals m2 over m1. And so I can think of this as d minus x over x quantity squared, because I'm just squaring the top and bottom. That equals m2 over m1. So let's think about this. I have, in my first term, d divided by x. And my second term is minus x over x, which is just 1. That whole thing is being squared. And that whole thing is equal to m2 divided by m1. Okay, so the next thing I should do is square root both sides. So I have d over x minus 1 equals the square root of m2 divided by m1. And in case you lost track, we're solving for x. That's what we're trying to do. So I have d divided by x, add 1 to both sides, is equal to 1 plus m2 over m1 under the radical. And the next thing I'm going to do is sort of cross-multiply, multiply on both sides by x, divide on both sides by this factor, 1 over square root m2 over m1. And we're solving for x now. X is d over 1 plus square root m2 over m1. And now we'll simply put the numbers in. Our distance, as I said, was 4.5 meters. Divide by 1 plus the square root of m2, which was 25 kilograms. Divide by m1, which was 15. And that gives us 1.96 meters. That's where you need to put the mass, m3, so that it has no overall force on it. And let's actually go back to the diagram and see that this makes sense. So the idea is, since m2 is a bigger mass, I have to have m3 further away from it so that the force of gravity is equal from m1. So I have to put it closer to the smaller mass to make the forces balance out. That's the idea. Okay? And then this is the last thing we'll talk about today, because so far we've really been in the theoretical world where we're talking about the force between two objects, and I just really want to emphasize that strictly speaking, we were talking about the force between two point masses. Okay, so when we have this force of gravity, which is g times m1 times m2 divided by r squared, we're assuming that m1 and m2 are two little point masses, so they have no size. Okay? So strictly speaking, that's what the law of universal gravitation is about, point masses. But in the real world, we're not talking about point masses, we're talking about really big objects like stars, planets, asteroids, etc. And those have some size to them. We can't really treat them just like little point masses. And just to give you a basic sense as to how you would treat a problem like this, so I have a little object over here, let's call it lowercase m, and then I have a big object over here, let's call it uppercase m, and I can't really treat this big object as if it's a little point mass, right? It's something like a star or planet, etc. The way to actually do this, it's kind of hard. I have to do an integral, meaning I'll take the force of gravity from this little part of the object, take the force of gravity from the next part of the object, take the force of gravity from the next part of the object. Basically, I'm breaking the object up into little pieces, adding up the force from all of those pieces together to give you the total force from the object itself. Okay, so that's called an integral. It's not something we're doing in this class because many of you haven't seen this yet. So don't worry about it. We're not doing integrals. So something that Newton realized is that, okay, the force of gravity from a big object with a complicated shape, let's say I wanted to calculate the force of gravity from your car, that would be kind of complicated because I'd have to do this big integral. But the way it works for spherical objects is actually kind of simple, okay? And fortunately, most celestial objects, like, again, stars and planets and moons, are spherical, okay? Okay, or at least almost spherical, right? I mean, the moon has a bunch of craters on it, the Earth is not a perfect sphere, but it's close enough, right? So here's what we have. The force of gravity from a spherically symmetric object is the same as if all of the mass were contained in a single point at the center of that spherical object. So what does this mean? Let's say I've got some object out here, maybe it's a satellite orbiting the Earth, right? And I'm trying to calculate the force of gravity that this spherical object exerts on this object. Well, we can treat it as if all of the mass of the spherical object is contained right at the center. So imagine it's all contained in a little point right at the center. It's exactly the same scenario, right? There's no difference between this spherical object exerting a force of gravity and then just a point at the center exerting a force of gravity. It's the same situation. So here's what we can do whenever we have a spherical object, okay? We can say the force of gravity is equal to big G times big M, that's going to be the big object here, times little m, that's going to be the little object over here, divided by r squared, where r is going to be the distance between little m and the center of big M. That's how this is going to work from here on out whenever we deal with spherical objects, okay? We're going to treat it as if all of the mass is just sitting there at the center. Okay, so that's it for today's lecture. When we come back, we're going to talk about some applications of all of this stuff, in particular circular orbits. How do satellites move around the Earth in a circular orbit? We're going to talk about how we know that 9.8 meters per second squared is the acceleration that things fall with near the surface of the Earth, and much, much more. So see you in the next one. In the meantime, be safe and healthy out there.